Hello everyone, I'm Joel Pampam here with my teammates Luke Shirath and Marcy Payne. Today we're presenting our research on map verification using signals and shapelets, advised by Dr. Allison Sullivan at UTA's Department of Computer Science and Engineering. Here's a quick roadmap of what we'll cover: the problems we're trying to solve, what time series shapelets are and why we chose them, our full approach, real results using UTA campus maps, and finally, our next steps. Historical maps are incredibly valuable. They give us a window into long term trends in urban development and environmental change, showing how cities grew and landscapes shifted over decades. The problem is that many of these maps exist only in physical form, and digitizing them is a balancing act between maintaining accuracy and keeping the process efficient. Errors can creep in at every step, and right now, every step requires manual review. So that brings us to our core research question: how can we systematically verify that a historical map has been accurately digitized? To answer that question, we turn to time series shapelets. A shapelet is a short subsection extracted from a time series representation of a shape. Rather than analyzing an entire sequence, shapelets focus on local structural features, the small but distinctive patterns that set one shape apart from another. By calculating the minimum distance between a shapelet and a given time series, we get a measurement that can identify and classify a shape, making the approach both efficient and interpretable. We specifically use logical shapelets, which incorporate speed up algorithms such as efficient distance computation, candidate pruning, and fast shapelet discovery, dramatically reducing time complexity and making the method scalable to large datasets. Logical shapelets are also significantly more accurate than classic shapelets and other state of the art techniques. Now let's walk through our methodology. Our pipeline has 8 steps. First, a physical historical map is captured in pixel form using a high resolution camera or scanner. That's our raster format. Next, we georeference it, binding the raster to a real world coordinate system by matching control points to their known coordinates. Then, features of interest are manually or automatically converted into polygon form through feature digitization. For each polygon, we calculate its centroid and draw hub lines connecting it to every boundary point. From those hub lines, we extract radial distance data, recording the angle and distance for each one. We then convert those values into a one-dimensional time series signal representing each map feature. From that signal, we extract a small distinctive subsequence, the shapelet, which serves as our comparison fingerprint. Finally, for verification, each map's distance to the learned shapelet is plotted. The smaller the distance, the more closely the digitized map aligns with the reference, and the more accurate the digitization. We applied this to a real historical maps of the UTA campus from 2025, 1992, and 1926. Each was run through our pipeline to produce a time series signal. Shapelets were extracted, and we plotted each map's distance to the learned shapelet. You can see how the signals evolve across eras and how the distance measurements reflect the structural differences between them. Looking ahead, we want to automate the georeferencing and feature digitization steps using computer vision, which would make the front end of our pipeline fully hands free. We also plan to test our methodology on maps from other cities and explore other machine learning shapelet approaches to push verification accuracy even further. In closing, we propose a signal based framework that converts two dimensional spatial features into one dimensional time series signals and extract distinctive shapelets for verification, offering a scalable, efficient pathway for automating historical maps digitization. Thank you.